So, good morning, good afternoon, good evening, depends on where you are in the world. So, thank you to join us today for another CASS talk. So, today we have the pleasure to have here Dr. Predo Toledo, that is working with Synopsys in Portugal. But before giving the floor to Pedro, just some announcements. So, if you lost some of the talks that were done since 2020. So we have more than 150 talks available in this YouTube channel, all for free. So this is a very nice set of very nice talks. As you should know, the next LASCAS, that is the flagship conference of CASS Society in Region 9, that means the International Conference of CASS in the region. Uh, Next one will be end of February, so the program will be a very nice one, and best papers are selected to have extended versions in TCAS 2 and TCAS 1. But as you can see, the deadline for submit papers is already gone. The papers were already selected. Then you can still consider also to prepare papers for the edition in 2026. But just to remind you that together with LASCAS, we also have collocated IBERCHIP, that is a workshop where you can also publish paper not only in English, but also in Spanish or in Portuguese. So LASCAS 2026 will be in Arequipa, in Peru, another very nice and interesting location to go. And the 2027 will be in Panama City. And now it's open the bid for the edition in 2028. So if you want to propose a location to organize the edition of 2028, take a look in your emails from CASS Society where the bid is distributed. Also, new is that end of April, we have the first edition of the Latin American Conference on Internet of Things. So this is sponsored by the IEEE Internet of Things technical community, and that is composed by 12 IEEE societies. CASS is one of the societies that is a major sponsor. So the extended deadline for submit papers is December 12th. So I hope that you will still submit a paper if you have not done yet. The second edition should be in Colombia, so it will go each year to a different location in Latin America now, with the participation of people all around the world, as it is a IEEE IoT-TC flagship conference. Then you have still a few months to prepare your papers to the next edition of SBCCI that will be in Manaus, so called Chip in the Jungle. So we have done a conference there in year 2000, so 25 years after. We'll be back to Manaus, a very interesting location also, with an interesting park of industry in electronics. So, and it's being prepared a very nice program to be an unforgettable one, as it was the edition of year 2000. But we are here today to attend the talk by Predo Toledo. So Predo Toledo is a member of IEEE, and he received the bachelor degree in electronic engineering from the Federal University of Pernambuco in Recife, northeast of Brazil, in 2010, and master degree in microelectronics from the Federal University of Rio Grande do Sul at Porto Alegre in 2015. He has completed a joint PhD degree with the Politecnico di Torino and the Federal University of Rio Grande do Sul, working in digital-based analog processing for IoT applications in 2021. He completed the IC Brazil program in 2011. He has also won the best 2015 Masters, and 2021 PhD thesis in the Design, CAD, and IC Test category from the Brazilian Society of Microelectronics, or Brazilian Microelectronics Society. His research interest includes electrical engineering, focusing on analog RF CMOS design and microelectronics education. He currently works as an RF AMS circuit designer at Synopsys with sub-10 nanometer CMOS technologies, FinFET, uh, arsenate of gallium, and nanosheet for high-performance computer. He's a member of IEEE Circuits and Systems Society and of the IEEE Solid State Circuit Society. So thank you again, Pedro, for accepting our invitation. And the floor is with you to start your presentation.
Okay, thank you very much for the invitation, Professor Ricardo Reis. It's nice to be back in at least virtually, in the Federal University of Rio Grande do Sul, where I did most of my career there. And it's an honor to be here in this big channel and in the CASS Society and show what I have done during until to my PhD, and I will show a little bit what I've been doing in the Synopsys a little bit. But the focus will be the title of this the title of this presentation, which was related to my PhD, which is the digital based operational transconductance amplifier, the evolution and the future perspectives of that. So the outline, the agenda of today is I'm gonna show a little brief boundary condition that we have now, the technology and the application background that we need to do it. After that, I will go to the digital based analog processing trend that we have been seeing in the nowadays. After that, I will focus on the main topic of the presentation, which is the digital based LTA, and after that, I will go through all the evolution of the digital based LTA, where we are now, and what are the future perspectives. Okay. So technology and application background and the IoT. Sooner or later we're gonna have a very strong protocol for IoT, so where several devices will be connected to the to the network, and the network will there are gonna be same very frames that you have to pass the information through it. And so the focus of the presentation will be in those edge device here, but now and what I've been doing in Synops is more related to this part here than the presentation today. So I will pass very quickly through those layers that we have been tackle in Synopsys. I will show a little bit what we do that, and after that I will focus on the principal and the main topic of the presentation. So Synopsys is everywhere. We if every technology that we see around the world, there is a touch of Synopsys on that, because if you don't use hardware from Synopsys or some IP for Synopsys, at least you have used some software from Synopsys to do your final hardware. So we can see that we can 100% sure that we are in everywhere. So Synops, there are several business unit, and I work in the IP development. So we developed a broadest portfolio of interface foundation IPs, and where I work is the file where we develop SERDER circuit, which is serialized, there are serialized circuits for communication. So this where the search this is in the is the high performance computer scenario where that several devices can exchange information. So we have to exchange this information as fast as possible. And the technology, the idea that do that is the SERDES circuit, and this is very simple block diagram that show what is SERDES is. We have a bunch of zeros and ones that represent information. We have to pass through a channel and we drive this channel, but this channel there is lost on that, and we have to recover, retrieve all the signal with some reasonable uh, rate of acceptance. So, and this is everywhere, and this is the broad portfolio of IPs that we do, and I've been working on those IPs so far. So PCI Express and USB and also M5, and now we have die-to-die communications. So uh, and what this is related to the IoT. In the end, is related to IoT because when the edge device catch the information using the best hardware that you can do it, you have to send this for a mainstream data center to post process this data, and this data is processed should be processed in parallel, and how to handle the exchange of information is through those IPs here, through those SERDER circuit. And if you are interested, last year we have published a very interesting paper where we show a circuit working 24 gigabytes per second, bits per second, the transceiver, where we show this is the kind of modulation that we use at PON4, and in the cut edge technology in FinFET 3 nanometers. And back to the main focus of the presentation. So we have to get information from the word, send to upwards to be processed with those nice features that we have been seeing in the nowadays, like artificial intelligence, of all those things that are fancy, and they are done in the data centers. So and this where the business where Synopsys work more on that. But before that, we have to get formation from the world, sense the world, and this is the focus of this presentation. Um, so those IoT devices on the edge of the network, they must to be tiny as possible, and to from centimeter cube to millimeter cube scale if possible. This is a publication, very famous publication, that showed that is possible. So the size as small as possible is the willing that we look for in those edge devices. Also, this kind of device should be energy autonomous, and it means that it uh, they they cannot draw too much current. They cannot waste too much power to do your uh, catch you're catching, gathering the information around the world, or to, doing some post processing in that in that in that edge device, because like we can see that if for several types of battery, and if we are in the microwatts domain, for instance, and we use a thin film battery like this, if we consume around 1 microwatts, this is gonna just last some few hours. Of course, we if we change for better battery, it can in microwatts we can enlarge this energy autonomous capability for weeks and years. But if we go to nano, even use those small thin film battery, we can enlarge the duration of the device. So the main takeaway here is to be to consume the lowest power as possible. Also, low cost, because those devices will be spread around the several application. So there must be a lot silicon uh, in, in several device. And the low area, it's to have a low area, it's a must. So as well as to do a fast design to reduce the time to market is also desirable, and also to be reconfigurable and power aware smart. It means that for instance, event-driven operation, it means that just work when it is needed, when there is an event to be processed or to be that cycle. So it means just to turn on and turn off in special moments. Those kind of features can save a lot of power, and those are the requirements that are needed to be found in those edge devices, because if you don't do that, the maintenance cost will be very large, and so nobody wants to have to change the battery every week. So if you if we can lower the cost and the power, we can the those devices can last years, so the cost of maintenance will be reduced a lot. So this just illustration how could be those edge devices, and what we can see that's as long as all the silicon processing has been tuned to achieve better performance in digital circuits. I could say that analog circuit, what regards the improvements of the processing of CMOS technology, has been put a little bit uh, aside, I would say, and this kind of circuits start to become a the main bottleneck, and so the we so there have been a lot of research on that, how to make those kind of analog circuit more efficient, and more uh, performable in those new technologies. And for instance, if you compare old process with a new CMOS process, the percentage of area of analog digital circuit has downscaled in 4 times, and so now analog become the critical part. So reduce this area has it turned out to be um, um, a must for us who like guys like me who work as a C design, analog IC design. Another thing that we have to struggle is the lower VDD for the newest technology. So we have lost the resolution in terms of current and voltage. So the VDD uh, has been down for just few hundreds of millivolts. However, the resolution time has been increased. So if we can translate the information that we process the analog signal in time instead of use the voltage, we could get the advantage of this for the analog circuit. And we're gonna show that when we translate the analog circuit to in the digital way to do it, what we are doing is that uh, in the backstage, what's happening is that we are doing the processing the time instead of use voltage or current. Okay, digital based analog processing trend is this is a survey that I did at the end of my PhD, and we can see the number of publication for digital intensive analog building blocks has been increasing along the years. So we can see that there is a trend to a visible trend that to do analog circuit just using analog digital stuff is has become how could I say advantageable. So um, so what is this concept in other words? This digital based analog process means that how can we process input signals that are coming in voltage or current modes from sensor, for instance, and with use a minimal, if needed, passive device either in the output or the output. How we could just use a digital circuit to do the same thing that analog block would do it, but just using digital circuits. This is the main concept of that. So general purpose digital based analog computer would be the final goal for research, that just use a digital circuit, do all the analog process that are needed. So we can see this trend is happening um, in several blocks. In PLL, it was the most we can find a lot PLL just using digital circuit, because the process the information is not naturally processing in time. So it's kind of natural to use just digital circuit. So those are the blocks that become the first one to use just digital circuit to do a analog process. But we can see that now we can find in the literature a lot of digital based on LDOs, for instance, where the power management is done just using digital circuits. Uh, that comes out to the main focus of this presentation, which is the digital based OTA. What is the OTA? Operational Transconductance Amplifier, which is a building block that is used in several applications, analog applications. So if we can make this circuit digitally, we can consequently we can put all several digital have several application in a digital format as well. So, but in order to understand how to do it, we have to go to the principles, and the principles of the OTAs is to amplifier a differential signal and and uh, uh, increase the current uh, with respect to the proportionally to have with respect to the differential signal of the input. So this is a kind of ideal Transconductance in the open loop, but we can see in the literature most of the application we use in the closed loop format, but in the open loop, this kind of behavior we it can be can be see here. And in the 2013 Professor Paulo Crovet has taught how we could translate this kind of behavior into a digital manner of see it. And but in order to do that, we have to understand what a simple OTA does in the analog manner, in analog way, and after understanding what it does, we can translate it to a digital. So sorry, and so what single digital DA does is simply to amplifier what the differential signal while reject the common mode signal. It means that when we have a common mode signal going up here, this current current source here, which ideally would have infinite resistance here, would would keep the same VGS for all the input transistor. So if we, buff nodes here increase at the same rate, the VGS of buff circuit is kept constant. In this way, we wouldn't have a net current in the output, so the commode signal would be reject. While if we have a differential signal, it means that this turned out to be a kind of virtual virtual ground, and in this situation, the VGS would increase a little bit for one side, it decrease a little bit for the other side, and in this way, after mirroring, those current would be sum up, and the output signal would increase and decrease according to the differential signal, while reject when we have just common mode signal. So here we can using a pseudo code translate this behavior, which is if the differential signal is larger than zero, we would we need to increase the V out, inject a charge here. If it is negative, we should decrease the V out, decharge this capacitor here. So basically, we have to perform this behavior here. If we analyze it in the digital way, I would say. How can we do that? We can start off with a couple of buffers, and we can see that just use a couple of buffers, we can infer how the circuit how the inputs are, what are the behavior of the inputs, and using that we can maybe realize a digital OTA. So let's start off with the first. We have four possible combinations for those outputs: 1100, 1001. And when we have, for instance, 1001, we can infer for the input that the differential signal is more relevant than the common mode signal, which is the difference between the average of the input to the thresh, the 3 point of those buffer here. And the same for this side here, and where we can see that the differential signal is way larger compared to the common mode signal, using the 3 point as a reference. And in this situation, we can came to this conclusion and say, okay, now we have a differential signal which is relevant, so we can use this formation to charge or discharge the output capacitance as we saw in the analog version. However, we have the other situation, which is 1100. And in this situation, in these both situations here, we cannot say nothing about the differential signal. However, we have information about the common mode signal. We can say that the differential signal, which is the difference between V plus and V minus, is lower than common mode signal, which is the difference between the average of the signal and the 3 point voltage of the buffer. So we can say that, oh, okay, in this scenario here, the common mode signal is more relevant, and we have to get rid of it, and we have to figure out a way to fix it, to fix this common mode, and make the circuit work in the other side of this table again. So we have to reduce the common mode. You have to in this case increase the common mode. In this case, decrease the common mode, and you make this circuit in this area again, and make more sensible to common mode differential signal and amplifier the signal as LTA should do. So, in summary, I will start off with this pseudocode here, and after that, I will translate to the circuit. So we can go to the easiest part, which is this one. When the circuit is 1 or 0 or 0 1, it means that the here in the input this differential signal is more relevant the common mode signal. So depending on the sign of the signal, we can charge or discharge this capacitor using this sorry, those transistor here, PMOS and NMOS. We can just implement a logic to catch this information from this and say, okay, if it is 1 0, we're gonna turn off this MN and turn on this MP and charge this capacitor. Otherwise, we would do the the they are not discharge this capacitor here. So it means that to turn off the MP transistor, it turn on the MN transistor. So this is very easy to understand. However, when we have, in this case, a common mode signal more relevant, we also have, we can catch this information and sum up with using some networking at the input. If we use the superposition theorem, we can see that this output here is the average of this input signal here and this input signal here and the common mode signal here. And doing that, we can, okay, if the 1 is appear here, it means that these voltages here are way above of the 3 point of the buffers. So we have to decrease this node here, and we sum up here. We're gonna put those nodes here be to more near to the 3 point and make the circuit more sensible to the differential signal instead of more sensible to the common mode signal. So in this way, we can charge, discharge this capacitor accordingly to the 1 and 0 information that we have here. In the end, what we are doing, if in the end what we are mimicking here is the same thing that the virtual ground does in the analog version. So we're gonna be tracking the common mode signal and correcting when we sum up here. Okay, so in order to illustrate here, when we have no differential signal, we can see that this circuit oscillates between 0, 0 and 1, 1. Uh, However, when there is a differential signal, there's gonna be a time interval that the signal of the input will be larger than the signal of one signal of input will be larger than another signal of another input, and we're gonna generate um, step signals that will increase the output accordingly, because we're gonna be in the state is 1, 0, 1, 0, 1, 0, 1, 0. So what is happening here is a kind of self oscillation track common mode circuit, and when there is a differential at input, this is catch, and this is caught by the circuit, and it is in the end there are gonna be several moments that those those differential signals are translated in time to pulse, and those pulse will be caught by the digital logic that I have shown before, and the charge discharge the output capacitor accordingly to the sign of the input. So this is the concept of the digital based OTA. So what about the evolution? What has been done as since the creation and until the nowadays? So the first version has been published by Professor Crovet from Polytechnic Torino, in the CASS 1, and he did using just off-the-shelf components, and that we can find in in the lab, or any lab, any educational lab in the in everywhere where there is a electronic course. And he did that, and he proved that the circuits work as a OTA, and he published. Of course, the performance was not so good because he used just components, and but when I got in contact with him, I proposed to him to integrate that. And at the time, there was the big trend to ultra low voltage. There is still actually the ultra low voltage circuits for IoT. And since those circuits is based on just digital circuit, it means that it works in very low voltages, because the standard cell, the logical gates work in very low voltage. So we decided to go to this direction, and we fabricated the circuit for the first time, if fully integrated actually. And we got surprised that we could perform the circuit work as an amplifier, as a OTA, just consume less than half of 1 nanowatt, and achieve of the best figure of merit at the time. And however, the application should be some sort just specific application like biomedical application where the bandwidth is not cannot be high bandwidth cannot be a requirement, a hard requirement, I would say. And we first we publish and using simulation, and after that with measurements. After that, we you can see it here. We have a struggle with calibration of those 3 point here. We had to put a kind of a network of transistor to calibrate the 3 point of this transistor because the 3 point uh, perform a main role of the circuit. So the offsets is mainly do it this is the offset of the circuit is related, is fully related to the offset of the 3 point between those buffer here. So we start to think at the time we start to think how to get rid of this some network, and at the same time create a first stage that could amplifier, and this way we could, when we refer this offset to input, it could be downsized by the gain of the first stage, and we got the solution uh, using Muller C standard cells. So in this way, we didn't need it anymore the any calibration, and it consumed a little bit more power, but we were able to achieve the lowest area for ultra low voltage OTA at the time. Uh, and we had published this in solid state circuit letters in 2010, 2020. And after that, some research groups around the world start to also make their own digital OTA. We can see the left view of this topology here, and also we can see the V in V out in the voltage follower configuration, and we can see that using this topology with this VDD, not so ultra low voltage, but for 550 millivolts, it's quite half of the VDD that we can, the nominal VDD that we can find in the nowadays technology. Just consuming 8 microwatts, it was able to achieve a very good GBW of 3 megahertz in a very small area. Those simulation here, those just was simulation results, but it showed to be a promising solution. I I hope to see measurements in the future. I also did an application for the GOTA. In this way, I also focus on biomedical application. We did a fully differential version of the DGOTA. In, but in the biomedical application, the noise it's a hard constraint spec, and in order to reduce the spec, we had to put 100 Muller C in parallel to increase the strength of the Muller C, and in this way reduce the noise, because the noise mainly the noise comes from the device of the input device. And doing that, there is a truth table to how to charge the charge, and also to track the common mode signal, the output common mode signal, and put in the right place. And we did that. We fabricated, and we can see that there is a gain because we're using the closed loop, and we can see the input, a very small signal here, and the signal being amplified, and we were able to get gains of 40 dB and reasonable CMRR and PSRR. Um, Also, and then my PhD, I had the privilege to do the last design of the digital TA, which we call time multiplex digital differential amplifier, but it works as LTA as well, where instead of using standard cell, we use a switch capacitor to do the same functionality that I have explained before. But in this case, we store the common mode information in this floatage voltage, and at the end, as we is it's happened in the digital OTA, the classical digital OTA, at the end we have to track the common mode signal here and make the signal just relevant to differential signal. And when we sum up, when we store the common mode signal here, when we do this signal minus this signal, we get rid of the common mode signal and let this signal to be just how could I say, um, uh, just dependent of the differential signal. And based on that, we can discharge or charge this output capacitor using negative voltage or positive voltage here put in parallel. So the big advantage of this circuit is that when we are doing the finished state machine to control all those switch here, we have realized that we have also the digital information of the differential signal here, and in the end we realized that we have done a kind of ADC, and we measured that, and this is when we use as a amplifier. So in this way, it was for 400 millivolts of VDD, just consuming 4.5 nanowatts. But the nice thing was that we could get um, a ADC with a reasonable performance. I did put here, but there is this is the power when we increase the VDD, okay, VDD scaling. But I forgot to put it here, but this ADCs, it works as ADC, and it's worked pretty well. We also try to research how those kind of technique would perform in another kind of technology, and we got in touch with a foundry that makes flexible circuits using TFT transistor, and we realized it was very interesting result that when we compare analog and a digital based LTA in those flexible technology, the digital LTA outperformed the analog one. So it was very surprising for us, and it has been published in the SEX 2022. These are some simulation results from this paper, where we could achieve 86 average of kilohertz of GBW, while the AC always above 35 dB. Recently, in 2020, a group from Roma has done a very nice work where they use a digital TA as an input, and a second stage uses just inverter-based uh, topology, and they use 28 nanometer CMOS technology. They were able to achieve a high DC gain compared to the previous results at the same VDD level, uh, and a reasonable GBW of 12 kilohertz. Um, this was nice result, and I'm looking for I'm look forward to see the measurement results, because in this paper just simulation result has been shown. Recently, in the International Flexible Electronics Technology Conference, a group from Portugal has done a digital OTA, but this in this topology they use a different logical family, digital logical family. Here he used a pseudo-CMOS technique, while in order to improve the offset, the buffers has been degenerated by a resistor. And for 600 nanometer TFT technology, and for a 50 picofarad of output, they were able to just consume a little bit above of 200 nanowatts, achieve reasonable DC gain and GBW. Recently, also here in Portugal, I have supervised a guy from Nova University, cooperation between Synopsys and Nova University. We saw that if we exchange, if we replace the inverter here by a Schmidt trigger, we could increase the size of the pulse that charge discharge this output here, and we could get the higher DC gain as well as GBW. And using FinFET technology, we were able to drive around 500 picofarad, a reasonable 25 kilohertz of GBW, and a DC gain above 40 dB, only consuming half micro watts. Future perspective of digital TA. We still don't know what were the limitation of those topologies. This would be a very nice research to do it. What is the limitation of digital TA? How much we can get advantage of this topology? Also, there are many applications that DigaTH can be used. I have been informed, but I cannot disclose here that for sensors, DigaTA has been used to 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 decrease the area of those sensors a lot. And in the future publication from groups around the world, you're gonna see that the DigaTA operating as a good sensor, as a good the thing that you are measuring to digital information. Also, I foresee multi-phase and multi-stage DLTA. You can see that in the plot that I have shown before. Most of the time, the output stage is in out impedance state, and high impedance state, sorry. And so if we put several DGOTAs in series in the same loop of oscillation, we can trigger the output more times, and so something called multi-phase DGOTA. This is something that could be explored. Also, try to translate those ideas to new technology that are coming, and those are the conclusions. And thank you. Those are the guys that I have worked with during my PhD, from Polito and Max Malioto from from Singapore University, Singapore University, EPFL, Professor Sandro Carrara, Bumpy, Professor Hamilton, who was my supervisor with Professor Paulo Crovetti, Shane from Macau, and Ana Kelly from sorry. Thank you very much, and I hope you had appreciated my presentation.
Thank you, Pedro, for this very nice talk. So, to the audience, so if you have more questions, please do it now using this chat channel. We have here one question from Gabriel Onzi. Is it possible to implement a digital instrumentation amplifier? Would it help solve common mode noise?
Yes, I think so. I think so. This you would be a very nice test case for digital amplifier to try to replace the amplifiers of instrumentation amplifier by digital ones and see what happened. And the of course this the instrumentation amplifier by natural by intrinsic behavior, it improves the common mode rejection. Use the DIG-OTA plus this, we would achieve a better common mode rejection. I think this it would be a good case of stud for that. Thank you, Gabriel, for the question.
Thank you. So I see no more questions in the chat. So I have one. Pedro, have you analyzed also, as you are working with low power circuits, their tolerance to radiation effects?
No, this would be nice because there are several techniques in digital how to handle those radiation effects. Since we are using digital logical gates, why not we could get some strategy that you guys have been using how to avoid the single event issues and from radiation. Why not? This would be a very nice uh, thing to be researched.
Yes, I think this is important nowadays as the circuits on the ground are also being affected by radiation. And if using
Hmm.
critical applications, you need to care this now. So, so no more question here. So, Pedro, thank you very much for your very nice, interesting talk. So I
Thank
hope to see you in person in uh, near future. Uh,
Yes, me too.
and before closing the session, I just would like to reinforce to all you that we have a first Latin American conference on Internet of Things. That means an international conference on Internet of Things from the perspective of different domains. As you can see, the IEEE IoT technical community is composed by 12 IEEE societies. And so you still have time to submit your papers as we have an extended deadline to December 12th. So, and I'm sure that there will be a very nice first edition. That means a historical one, no? So the first one, if you want to be the history of the event, you should submit it to this first edition. No? And soon we are now to some next CASS talks. So thank you very much to all you that attended this presentation of Pedro, and thank you again, Pedro, for your very nice talk. And so see you soon in a new CASS talk. Bye bye.
Bye bye. See you. Thank you very much, everybody. Have a nice